All right, so in this last trig unit, all right, we're going to be talking about mostly identities and equations. All right, so a lot of this stuff we've already done as far as evaluating trig functions and simplifying trig expressions. Well, we will be doing a lot of simplifying trig expressions today. All right, but we'll also get into trig identities, especially verifying them a lot more tomorrow, and then we'll jump into solving trigonometric equations after that. Okay, so you should already have all of these somewhere, right? But if you don't, you would definitely like to have them all on one page that's easily accessible in your notes. All right, so we know about all of our reciprocal identities. All right, so sine of u is the reciprocal of cosecant, so equals 1 over cosecant u, which means cosecant of u is equal to 1 over sine of u. Cosine and secant are reciprocals, so cosine of u is equal to 1 over secant of u, and secant of u is equal to 1 over cosine of u. And last but not least, try to give myself a little bit of room over there. All right, of course, tangent and cotangent are reciprocals as well. So tangent of u is 1 over cotan u, and cotan u is 1 over tangent of u. So those we should have pretty well down at this point, right? We've been using them for quite some time. All right, quotient identities. We've talked about these a couple of times, especially they were very useful in helping us find some of our asymptotes and help with our domains and stuff with tangent and cotangent in our last unit. All right, so tangent of u is equal to sine of u over cosine of u. And cotangent of u, we know that it's the reciprocal of tangent, so we know that this is just cosine of u over sine of u. So this is just a refreshing of all of our identities thus far. All right, so we have our Pythagorean identities as well. All right, sine squared u plus cosine squared u is equal to 1. All right, 1 plus tan squared u is equal to secant squared u. And 1 plus cotangent squared u is equal to cosecant squared u. All right, do remember, just as a side note, right, that for instance, sine squared of u is really just sine of u all squared. All right, but remember they write it like this because sine squared of u is not equal to sine of u squared. Why are these things different?
Because the u is getting squared.
Right. Here, only the u, the argument of sine, is being squared. Whereas up here, the whole sine of u is being squared. So, for instance, sine of u squared is simply equal to sine of u times u, right? Or u squared. All right. Whereas sine squared u is equal to sine of u times sine of u, right, which are very different things. All right, so do note what this squared means. All All right, co-function identities. They're called co-function identities because they always match with the co's. All right, so sine of pi over u minus u, or pi over 2 minus u, is equal, since this is sine, this is equal to cosine of u. All right, since this is tangent, this is equal to cotangent of u. Since this is secant, this is equal to cosecant of u. All right, now this is pi over 2, so this is obviously in radians. This works the same as if this were 90 degrees, okay? So do be mindful of the conversion between radians and degrees, of course. All right, and here, of course, cosine of pi over 2 minus u is equal to sine of u, right? Sine and cosine, right? Cotangent and tangent, all right? And cosecant and secant. These aren't used terribly often, but every once in a while there's some specific cases where they can be useful. All right. We also have our even-odd identities. Remember, with even functions, the negative just kind of goes away. And with odd functions, it shows itself out in front. So sine is an odd function. So this would become negative sine of u. All right. Of course, the reciprocal functions are the same as far as odd or even. So since sine is odd, cosecant is odd also, so the negative will come through here as well. Cosine here is an even function, so when you plug a negative argument into an even function, it just kind of disappears. So this is just cosine of u. Of course, secant is the reciprocal of cosine, so if cosine is even, so is secant. So the negative will go away here as well. Tangent is an odd function, so the negative will show itself out front here. And of course, cotangent is the reciprocal of tangent, so cotangent is odd as well, so the negative will come through. All right. So use the value of secant of u being equal to negative 3/2 and the fact that tangent of u is greater than 0 to find the values of the other 5 trig functions. Okay, we've done this before, but we've always made triangles, right? Now we're just solely going to use identities, all right? So we need to find sine of u, cosine of u, tangent of u, cosecant of u. We've already been given secant, so you don't have to find it. You can write it down again if you want, but you certainly don't have to. And cotangent of u. All right, what's the really easy one to find? Cosine, right? Cosine is simply the reciprocal of secant. So I know that this is negative 3/2. All right, well, now I need to look at all of my identities, and I need to say, okay, well, I need to find an identity where I have everything except one, right? You can only have one missing piece. Yes, you're right. Where I have everything but one, right? You can only have one missing thing if you're going to solve for it. All right. So can anybody of all of those identities that we just looked at find an identity where we have everything but one piece? And there's a couple of them that you could use. All right, so let's go through. Do we have any negative arguments anywhere? All right. We do, but they only help you find themselves, right? Like, okay, well, if I have, secant of negative u, okay, well, then that's secant of u. Okay, awesome, but that doesn't help me because I already have secant of u, right? So those aren't going to help. Right? We certainly don't have anything that looks like this, right? So that's not going to help us. All right, can any of these help me? So here, for instance, sine squared u plus cosine squared u is equal to 1. Do I have either sine or cosine? Yeah, we have cosine. We don't have sine, but that's fine. Do I only have one missing piece? Yeah, right. If I have cosine, the only thing that I don't have is sine. So absolutely, we can go ahead and use that. All right, we can say, all right, well, sine squared u plus cosine squared u is equal to 1. All right, well, we don't know sine. That's what we're looking for. All right, we do know cosine. So if cosine of u is negative 2/3, then cosine squared of u is negative 2/3 squared. All right, so sine squared u plus this negative 2/3 times negative 2/3 would be positive 4/9. So I'll change this one to 9/9 to make my math easier. All right, well, now I can subtract 4/9 from both sides. How do I undo a square? Square root, yes, thank you. All right, so you take the square root of both sides, and here we get sine of u is equal to, when you take the square root of a fraction, you take the square root of the numerator over the square root of the denominator. All right, now when you take a square root of something, it's technically plus or minus, right? So we have to determine, are we going to use the positive or negative root? All right. Well, it tells me here secant, which means cosine, is negative, but tangent is positive. What quadrant, do you remember our all students take calculus, right? What quadrant is cosine negative and tangent positive? Quadrant 3. See, because the tangent is positive. Here it says tangent of u is greater than 0, right? Whatever letters in here means that's what's positive. Right, of course. Agreed. Yeah. So we know that we're in quadrant 3, and quadrant 3 is sine positive or negative? Negative, right? Does sine begin with t? Nope. Then it's not positive, right? So here it has to be negative. So I know that sine of u is negative square root of 5 over 3. All right, now for cosecant, I'm going to have to flip that, but I'm also going to have to rationalize it. So this is going to be negative 3 square roots of 5 over 5. Okay, so all I need now are tangent and cotangent. All right, there's multiple different ways that we could do this. All right, we could use either one of these, right, because I have secant and I have cosecant. All right, so I could use either of those. That would be fine. I think these are actually a little bit easier. All right. Um, I'll go ahead and just use this one since it's the first one, right? So tangent of u is equal to sine of u over cosine of u. So I can simply say tangent of u is equal to sine of u, which is negative root 5 over 3, over cosine of u, which is negative 2/3. Well, of course, my negatives will cancel out, and these 3's will cancel out. So this is simply the square root of 5 over 2. So if I flip that, I'm going to have to rationalize it, and this would be 2 square roots of 5 over 5 once I do that. And we're done. We have found the other 5 trig functions simply from being given 1. Good times? Had by somebody somewhere? Alex is having good times. Rocking out over here. All right. Why don't you guys try this one? It will work very similarly. All right, so use the value of sine of u is equal to 2/5, and that cosine of u is less than 0. All right, so it's saying we know that sine is positive and cosine is negative. All right, so that really just helps us with sines. What quadrant are we in here? Second quadrant. Very good, Jasmine. All right, so we will be in the second quadrant. All right, we know sine. All right, so we will need to find cosine, tangent, cosecant, secant, and cotangent. Right, so go ahead and do what you can. I'll give you a couple of minutes. Okay, so if we take a look at these things, all right, we know that sine of u is 2/5, so we automatically know that cosecant of u is 5/2. Again, since we already have sine, we can go ahead and use sine squared theta, which will be 4/25, plus cosine squared theta, or u in this case, is going to equal 1, which is 25/25. So if I subtract 4/25 from both sides, cosine squared u is equal to 21/25. Take the square root of both sides, and cosine u is equal to the square root of 21/5. Now, of course, again, this can be positive or negative. It tells us here that cosine is less than 0, which means that has to be negative. So this will be negative square root of 21/5. All right, so for secant of theta, we can just flip that. Of course, we'll have to rationalize it. So this will be negative 5√21/21. All right. When you have sine and cosine, it's easy enough to find tangent. All right, so we know that tangent of u is equal to sine, which is 2/5, divided by cosine, which is negative root 21/5. So of course, these 5's will cancel, and we would have to rationalize this, right? So this would be negative 2√21/21. Of course, you can just flip this. Of course, it's easier to flip this pre-rationalized, right? So you just flip this and you get negative square root of 21/2. And there's our 5 missing trig functions, so we are in good shape. Okay, so now we're going to get to simply just simplifying, right? So we want to get these basically as compact and simple as we can, all right? So we're going to have to, use our identities to just kind of rearrange things and get them to look nice and clean, all right? What do we notice about both of these pieces here? All right, both of these terms. Do they have anything in common? There's a sign, right? There's a sine x in both terms, all right? So that's a common factor, which means I can go ahead and factor that out. Right? And if I do, right, here I'm left with cosine squared x, and then here I took everything out, so that just becomes a -1 for the placeholder. All right. Well, this looks kind of like something that we have, right? one of our identities says sine squared u plus cosine squared u is equal to 1. What would I have to do to get one side of this equation to look like this? A couple of things, right? So basically, I'm going to subtract sine squared u, right, from both sides. And then I'm going to subtract 1 from both sides. All right, so when I do that, this cancels and this cancels. All right, on this side, I'm left with cosine squared u minus 1. And on this side, I'm just left with negative sine squared u. All right, so we are allowed, just like any equation, we're allowed to manipulate it, right? As long as you keep it balanced and do the same thing to both sides, all right, then you're allowed to alter it to suit your needs. All right, well, remember in mathematics, whenever two things are equal, they are completely interchangeable, all right? So cosine squared x minus 1 is equal to what? Yeah, x in this case because we're dealing with x's, but yes, negative sine squared x. So I can replace this whole piece here with negative sine squared x. All right, now what is x times x squared? Not a trick question, pre-algebra, right? Like literally pre-algebra class, so 6th grade for a lot of you. What is x times x squared? Yeah, x cubed. Yeah, that wasn't a trick question. I wasn't trying to mess with you guys, right? So x times x squared, right? You add the exponents here, and this becomes x cubed. All right. So what do we think sine x times sine squared x is? Sine cubed x. And then, of course, a positive times a negative is a negative. So this just equals negative sine cubed x. That looks pretty simple to me, right? One nice term, we're done. All right, now obviously this was just to refresh those of you that don't remember anything about algebra, right? But like anything like this that you do to help you, that's just side work. You don't need to include it like in the main body of your, your work. It's perfectly fine to just do it off to the side. All right, very similar concept here. Why don't you guys go ahead and try that? Hmm. Okay, so this shouldn't be too bad, primarily because a lot of it is very similar to what we just did, right? So again, both of these have a cosecant x, so I can go ahead and factor that out. And when I do, I'm left with cosine squared x, and then again minus 1 here for the placeholder since I took everything out. That's exactly what I had here, right? So I know that that's just going to be switched with negative sine squared x. Also, cosecant x is 1 over sine x. And this is negative sine squared x. Well, what do we think is going to happen if I have 2 sine x's in the numerator and 1 in the denominator? What happens if I have x squared over x? Yes, right? Because think about it, x squared is x times x. So of course, 1x in the bottom cancels with one of the x's in the top, and you're just left with x. Same thing happens here, right? So this is simply negative sine x. Done. Okay, so now we're going to factor, all right? So sometimes it will help to use our familiar trick that we use quite a bit in this course, right? U substitution, all right? So for instance, if I just let cosine of x equal u, right? And really I should have done that the other way around, but that's fine. Then u squared is equal to cosine squared x. All right, so if I do that, I can simply rewrite it like this. Now, this is a difference of perfect squares. We have factored this a million times since Algebra 1. All right, so this would just factor to 1 plus u, 1 minus u. But I'm not really talking about u's here. What is u? Cosine of x. So this is really 1 plus cosine x, 1 minus cosine x. All right, now, you don't have to do this u stuff, right? It's quite plausible and even easy to look at this and say, oh, this is a difference of perfect squares, right? And jump straight to here. That's perfectly fine, but not all of us can see it that way, right? So sometimes it does help to put it into a form that we're more comfortable with or that we are more used to seeing. Fair enough? All right, try this one. It obviously will work very similarly. All right, so this goes very quickly, right? Um, Especially if you don't use the u thing. Of course, you could let u equal secant theta, and then u squared would equal secant squared. No, I'm sorry. Yeah, would equal secant squared theta. So then you could just substitute that here. But again, this is very easily seen as just the difference of perfect squares. So here you will just have secant theta plus 1 and secant theta minus 1. Done. Factored. And again, if you don't see that and you want to use the u, that's perfectly fine. You just say, okay, well, let's let u equal secant of theta. Therefore, u squared would equal secant squared theta. And you would end up with u squared minus 1, which would factor to u plus 1, u minus 1. And then, of course, you just substitute back in the secant theta for u, and you end up right back where we are here. Okay, so same concept here, except now, all right, we're dealing with trinomials instead of a difference of perfect squares. All right, but again, we can use that same little trick. Say, okay, well, let's let u equal tangent of theta. All right, therefore, we know that u squared would equal tangent squared theta. So we substitute that back in, and now this is 4u squared plus u minus 3. This looks just like a nice ordinary quadratic. All right, so we can do our, now this has an a other than 1, so I'm going to go ahead and use my trash can method here. Remember, a times c, that gives me negative 12, and b gives me 1. So I need two numbers that when I multiply them together give me negative 12, and when I add them together they give me positive 1. All right, so that's going to be 4 and negative 3. All right, 4 times negative 3 is negative 12. 4 plus negative 3 is positive 1. All right, so I keep my leading coefficient here and my variable. So I have 4u and 4u. And I fill it in with what I just found here. So a positive 4 and a negative 3. All right, well, when our a is something other than 1, we aren't done. All right, we have to do that taking out the trash step. All right, so I say, all right, is there any common factor between these two terms here? Sure, I can pull out a 4, and I'm left with u plus 1. Is there any common factors here? No, there are not. So I have to leave it for u minus 3. And whatever I pull out in this step, that's why we call it taking out the trash, we just throw it away. All right, so this is my factorization. Of course, I'm not talking about u's. My u is tan theta. All right, so this is tan theta plus 1. And 4 tan theta minus 3. And of course, you can always check yourself by actually distributing these out, combining like terms, right? And if you don't get back where you started, then obviously you did it incorrectly. So yet another time when factoring is incredibly important in mathematics. Try to stress to all of my Algebra 1 kids how important it is to learn to factor and how much easier it will make the rest of your mathematical career. All right, but most of them don't pay attention to it. All right, so go ahead and try this. It will work much the same. All right, so we do the same thing here, right? We say, all right, well, u can be secant of theta. So u squared will be secant squared theta. So this becomes 2u squared minus 7u plus 6. All right, so again, I'm going to do my trash can method here. 2 times 6 is 12, and negative 7. All right, so two numbers that multiply together to give me 12, add together to give me negative 7, are negative 4 and negative 3. So I keep my leading coefficient here, and I fill in my blanks with the numbers I just found, negative 4 and negative 3. All right, again, I'm going to have to take out some trash. So I look at my first factor here. Both terms have a 2, so I can pull a 2 out, and I'm left with u minus 2. I can't pull anything out here, so 2u minus 3. All right, so these, whatever we pull out, we throw away. This is my factorization. Of course, I'm not dealing with u's, I'm dealing with secant theta. All right, so this is secant theta minus 2 and 2 secant theta minus 3. And we are factored, we are done. All right, now what do we notice about this one that's different than the two previous we've seen? Yeah, they're too different, all right? And we don't like that, right? So what we're going to have to do is we're going to have to change one of them, and we're going to have to use one of our identities. All right, now, just as a kind of a side note here, whenever you're doing these, you're always going to change the squared one, every time, all right? Now, we have an identity, all right, that says 1 plus tangent squared theta is equal to secant squared theta. All right, so wherever I see one of these, which I see a secant squared, I can replace it with this. All right, so I can change secant squared x to 1 plus tan squared x. All right, then I still have my plus 3 tan x plus 1. All right, well, now I have these common like terms here, right, both of my constant terms. So this really becomes tan squared x plus 3 tan x plus 2. Again, if you really want to, you can think of this as u squared plus 3u plus 2. And especially since my leading coefficient is 1 here, it's quite easy. All right, this just ends up being tan x plus 1 and tan x plus 2. Right, this, of course, would just be u plus 1, u plus 2. All right, so whenever you have that case where your trig function that's being squared is different than your first degree trig function, you're always going to use a Pythagorean identity. Okay, always. And why don't you guys try one? right, so here again, of course, one of our Pythagorean identities says that 1 plus cotangent squared theta is equal to cosecant squared theta. All right, so of course I can replace my cosecant squared here with 1 plus cotangent squared. I still have my minus cotangent x minus 3. Again, I have to combine like terms here. So I end up with cotan squared x minus cotan x minus 2. Of course, if you really want, you can write that as u squared minus u minus 2, which of course factors to u minus 2 and u plus 1. So this just becomes cotangent x minus 2 and cotangent x plus 1. And that is it. All right. All right, so here, all right, we're kind of still working with a lot here. We're just going to be simplifying. All right, now one kind of rule of thumb doesn't always work, but it works most of the time when you're trying to simplify. All right, when simplifying or verifying, trig identities, put everything in terms of sine and cosine. And it typically helps. All right, so cosecant of t, we know we can rewrite that as 1 over sine of t. All right, minus cosine is already in terms of sine or cosine. And cotangent, all right, is cosine of t over sine of t. All right, so now we can go ahead and multiply these, right? You can think of this as over 1 and just multiply across the top, multiply across the bottom. So then we have 1 over sine of t minus cosine times cosine is cosine squared t over sine t. All right, now they have a common denominator. So when they have a common denominator, we can combine the numerators and keep that denominator. So this will just be equal to 1 minus cosine squared t over sine of t. All right, what should this remind us of whenever we see a 1 and a trig function squared? What kind of identities? The Pythagorean identities. All right, and specifically with this one, the one that says sine squared theta plus cosine squared theta is equal to 1. Well, how can I get one side of the equal sign to look like 1 minus cosine squared? Simply subtract cosine squared, right? When I do that, these cancel. So now I have sine squared theta is equal to 1 minus cosine squared theta. Oh, hey, yay, I can replace this. All right, so this is the same thing as sine squared t over sine of t. And what happens when I have 2 up top and 1 in the bottom? Yeah. So this is just sine of angle t. Cool beans? Beans are cool. All right. That's the one I just did, right? Yes. All right. So now let's rewrite this, all right, so that the expression is not in fractional form. Okay. Now, um, you should have seen this in Algebra 2 a lot when dealing with complex numbers. All right. It was called the complex conjugate. All right. You'll use it in calculus when you use the definition of derivative to find derivatives of square roots, radical functions. All right. And it's just a little trick that's kind of often used in mathematics. All right. Whenever you have some denominator thing that you're trying to clear out, all right, you typically want to multiply by what's called the conjugate. Okay. Now, the conjugate, right, which you should have talked about it in terms of the complex conjugate when you were dealing with, the quadratic formula and all that stuff in Algebra 2. All right. But all you have to do is change this sign. All right. So I'm going to multiply the denominator by 1 minus sine of x. And then, of course, to keep it the same, whatever I multiply the bottom by, I have to multiply the top by as well. All right, so now when I do that, I get 1 minus sine of x over, all right, and this is a difference of perfect squares now, right, like the factored form of it. So when you multiply this out, it's actually going to end up being 1 minus sine squared x. Coming to get them, huh, bud?
Yep.
Just throw those papers anywhere. You can put them right on that just computer desk right over there. I'll get them. Right? Did they play well? I didn't see it. Ooh. Okay. Yeah, that's not good. I mean, did they even make it to?
Yeah.
Okay.
Four, maybe. 4 out of 5.
Oh, I gotcha. So they made it as individuals instead.
No. 4 out of 5.
Oh, 4 out of the team. Oh, God. Okay. I gotcha. Wow. I mean, could they make it any easier? Could they make it any easier to make it?
But then they have to play Shaq's good. Yeah, they have to play it again Monday.
Yeah.
They just don't like that.
Jake said he hates that course. He said it's in terrible shape.
Jake made all these.
Good. All right. So we've got 1 minus sine squared x here. All right. That's very similar to what we did here, right? Except now we're doing it the other way. All right. So if we have sine squared x plus cosine squared x is equal to 1, if I subtract sine squared x from both sides, I get this. All right, which means I'm allowed to replace 1 minus sine squared x with cosine squared x. So now I have 1 minus sine x over cosine squared x. Okay, well, just like when things have a common denominator, you can combine them together, all right? You can also go the opposite direction and kind of pull them apart, all right? So I can actually go ahead and say, okay, well, this is really 1 over cosine squared x minus sine x over cosine squared x. All right. I can even take it a little bit further. All right. And 1 over cosine x is secant x, right? Well, it works that way with higher powers also. So this is just secant squared x. All right. Now, what I'm going to do here is kind of change this around a little bit. I'm going to keep this sine x up here. All right, but I'm going to multiply it by 1. Does that change anything? No. Multiplying something by 1 keeps it the same. All right, and down here, I'm going to break this cosine squared x up to have it cosine x times cosine x. All right, well, now I can kind of think of these as two separate pieces. All right, what is sine x over cosine x? Say that again. Tan x, absolutely. And what is 1 over cosine x? Yeah. Do I have a fraction anymore? No, right? And all this thing said is rewrite it so that it doesn't have a fraction. That's good enough. As soon as you get to where there's no fractions, you're done. So that had kind of a lot going on. You had to know a couple of little tricks and things to use. One over cosine squared x, right? We know that 1 over cosine x is equal to secant x, right? Well, it works the same way with higher powers, no matter what, okay? Now, the reason why is because kind of similar to what we did here, right? You could definitely just say, okay, well, I'm going to multiply that 1 times 1 again. And I'm going to change cosine x to cosine x times, or cosine squared x to cosine x times cosine x, right? And then, oh, well, I really have two separate pieces here. So this is secant x times secant x, which is really just secant squared x, right? But you don't have to go through all of this every time, right? You can just say, oh, okay, well, reciprocal functions work the same way no matter what the power is. So it wouldn't matter if it was 1 over cosine to the 10th x, right? That would still just be equal secant to the 10th x. Does that make sense? Okay. So that's why we were allowed to do that. All right, try this one. It will work much the same. So of course this works pretty much the exact same, right? We multiply by the conjugate. So we have to do that same thing to the top. All right. So then we end up getting cosine squared y times 1 plus sine y over 1 minus sine squared. All right, well, the 1 minus sine squared is that same thing that we had last time where it's just cosine squared, and this should make this a y just for consistency purposes here. All right, so now this just becomes cosine squared y times 1 plus sine y over cosine squared y. So that'll just cancel. Well, now there's no more fraction. We're done. All right. All right. Use the substitution. X is equal to 2 times the tangent of theta, for theta being in the first quadrant, to write the square root of 4 plus x squared as a trig function of theta. Okay, so a lot easier than what it sounds, all right? We literally just, again, when two things are equal in math, they're interchangeable. So I'm going to go ahead and plug this in here, all right? So this will be 4 plus, and then we have 2 tan theta quantity squared. So all I did was simply plug 2 tan theta in for x. All right, well now we get 4 plus, all right, when you actually square this, 2 tan theta times 2 tan theta, you get 4 tan squared theta. Okay, now, do not make the mistake of just saying that you can take the square root of both of these pieces. You cannot because of this plus here. Right? That works with multiplication and division. It does not work with addition and subtraction. So what we actually have to do first is factor out a 4, and then we'll be left with 1 plus tan squared theta. All right, well, one of our Pythagorean identities says that 1 plus tan squared theta is equal to secant squared theta. So now this is just 4 times secant squared theta. Well, now we got rid of that pesky plus sign that was preventing us from just taking the square root. All right. Now, like I said, with multiplication and division, you can just take the square root of both pieces. So the square root of 4 is 2. The square root of secant squared theta is just secant theta. And that's it. All right, so the directions make that appear to be much more difficult than what it really is. All right, go ahead and try this one. It will work the same way. All right, so again, we just take what my x equals and I plug it in for x. So we end up with 25 minus 5 sine theta quantity squared, which then will equal the square root of 25 minus 25 sine squared theta. Again, I don't like this minus sign in there. All right, so I'm going to factor out a 25. And that will leave me with 1 minus sine squared theta. All right, which if we manipulate the Pythagorean theorem around a little bit, this will just be cosine squared theta. Which again, that got rid of that annoying subtraction sign. So now I can just take the square root of both pieces. So 5 cosine theta. And that's it. All right, that's all for today. You have an assignment on Delta Math that you can use the rest of the block to get started on. It's just simplifying, so it doesn't cover all of the various types of problems we went over today. It's really just simplifying trigonometric expressions. So do remember it can be very useful to put everything in terms of sine and cosine when you do that. It's not going to work for you every time, or sometimes it'll make it a little bit more difficult than what it needs to be. Sometimes you can just see a very easy way to do it, but in general, if you get stuck, try to put everything in terms of sine and cosine.